where it is, you may not be able to determine how fast they're moving. So things start to change when you get into the microscopic world. So in this case, a lot of work done by many famous physicists, and discovered that the subatomic particles, the present condition, does not always determine the future condition. And this is also things are behaving differently in the microscopic world. Okay, so that's how the quantum mechanics theory started. And the quantum mechanics forms the foundation of modern chemistry. Everything that we understand is based on the theory of quantum mechanics. And it explains how and why we organize the periodic table. We have 118 known elements so far to this day. And you put them in a particular order. Anything when you do that changes that order is incorrect. Well, quantum mechanics theory will explain why those things need to be listed in that order. Okay? Now, we were talking about the significance of the group when we introduce the periodic table. We say the elements in the same column in the same group behaves similarly. So they are going to have similar type of chemical reaction. And we mentioned that. And while in the afternoon class there, one was saying, what's the significance of the period? And I never thought about that. So I stumbled on that question for a while, and then until I realized, well, the significance of the period is that elements in the same period, their atomic number is increasing by 1 proton at a time. So, and then the whole series of numbers repeat itself periodically. So when you go from group 1A all the way to group 18A, group 1 all the way to group 18, and then you start with group 1 again and go all the way to group 18. Okay? So the importance of the period there is that for elements within the same period, you have an increasing number of atomic numbers. So you have an increasing atomic number lined up. You cannot switch the position, because the elements that we have in each period has a fixed number of protons in there, a fixed number of electrons in there. They may have different number of neutrons, okay, for the same atoms, but that's okay. I mean, you cannot switch, say, iron from zinc, because, well, you have to arrange them in increasing order. Okay? So the behavior of elements in chemical bonding can be explained with the quantum mechanics theory, and then we also quantum mechanics also provide basic practical basis for lasers and everything that we know of in modern chemistry. Your touchpad and your iPhone, it's all based on our understanding there. At that time, a group of scientific genius, Albert Einstein, Niels Bohr, Louis de Broglie, and Max Planck, and Heisenberg, and Schrödinger, they worked independently and collectively to develop the quantum mechanics there. And that is the foundation of modern chemistry. So the behavior of the very small particle, electrons are incredibly small. Okay? A single peck of dust has more electrons than the number of people who have ever lived on Earth. So remember that number, 6.02 times 10 to the 23. And I gave you that example, and I did not know how many of you actually did the calculation. If you have a computer, when we talk about the number of moles there, and say, if you try to count the atoms out, and you have a computer that can count 10 million atoms per second, it would take 1 billion years to count out 1 mole of an atom. So that's a huge number there. Electrons are much, much smaller because, say, 1 gram of hydrogen atoms, it contains 6.02 times 10 to the 23, that many particles there. So if you divide that number, the total number, by the total mass there, you get the mass of each electron or each molecule or each atom there, and those numbers are, in grams, are extremely small. And electron behavior actually determines the behavior of the atom there. So we cannot observe subatomic particles, or for that matter, we can't even observe directly the behavior of an atom. Okay, and so the electrons are so small. If you try to observe it, well, you have to shine light on it. The radiation light is actually going to change the behavior. Shining light on an electron would affect the pure existence, the state of the existence of the electron there. So that's something that started to, scientists at that time, around the turn of the 20th century, scientists started to make the observations there and then trying to explain what we observed in the laboratory there. So in that period of time, the formulation of quantum mechanics takes place. And that is the basis of everything that we know about this world. And so the quantum mechanics model explains the manner in which electrons exist and behave in atoms, and also helps us to understand and predict the property. All things that we do, all the things that we're trying to do in scientific research is that we're trying to study what we have at hand so that we can make predictions. We don't have all the time and resource to understand every single reaction for every single element and atoms of element that exists. But once we have that periodic table, well, we don't have to study the reaction between potassium and chlorine. If we know the reaction between sodium and chlorine, sodium and potassium belongs to the same group. They're going to behave the same way. And you're going to end up with sodium chloride, potassium chloride. So we can make predictions there. Okay, and so some elements, going back to the second chapter, there we're talking about metals and non-metals. Why are certain elements are metals? Why are certain elements are non-metals? Why do metals gain electron? I mean, lose its electron, and non-metal gains electron there. And some are very reactive. Some are not as reactive. What determines the behavior of the atom? Well, electron distribution. Electron distribution is understanding electron distribution. We have to understand the quantum mechanics model there. Okay, so we have several learning objectives, and again, as I said at the beginning, the intention and the scope of this particular class is not to get into the details about the quantum mechanics there. So we're going to introduce the basic theory. We don't need you to do any calculation that involves the details of the quantum mechanics. There are only 3 equations that we need you to remember for this part of the lecture there. So we're going to first look at what we call the electromagnetic radiation, or simply light. And when you see light, that's an electromagnetic radiation. What's the relationship among these different quantities involved in electromagnetic radiation? Wavelength, frequency, velocity. Now we know light travels, or electromagnetic radiation travels at a constant speed. We call it speed of light. It's 3.00 times 10 to the 8 meters per second. That's very high speed. And so far we say, well, nothing travels faster than the speed of light. That theory is being modified to some extent with the current research. Some of the physicists claim that they have discovered particles that travels faster than the speed of light. But so far, there's not overwhelming evidence to prove that. And so for the scope of this course there, I'm going to say, well, light travels at a constant speed. And that's the fastest speed we can ever achieve. Okay? So we are going to study electromagnetic radiation. We try to discuss in this particular learning objective. This is a fairly large learning objective there, and basically covers the basics of the quantum mechanics there. So we're talking about particles. We're talking about electrons, protons, and neutrons, very small particles. And we introduce what we call wave-particle duality. Right? And there's a wave nature of little particles. There's